Hello, this is Dr. Devasish Dangar. Today I am going to discuss replacement theorem, which is very famous in vector space of linear algebra. The theorem states that if set alpha 1, alpha 2, alpha n be a basis of a vector space V over a field F and a non-zero vector beta of capital V is expressed as beta equal C1 alpha 1 plus C2 alpha 2 plus Cn alpha n, comma, where Ci's are belongs to F field. Then if Cj not equals to 0, the set alpha 1 alpha 2 alpha j minus 1 comma beta comma alpha j plus 1 comma alpha n set close is a new basis of V. That is, beta vector can be replaced alpha j in that basis. To prove of this theorem, uh, given that beta c1 alpha 1 plus c2 alpha 2 plus plus cj minus 1 alpha j minus 1 plus cj alpha j plus cj plus 1 plus alpha j plus 1 plus cn alpha n, or cj alpha j we can rearrange cj alpha j equal beta minus c1 alpha 1 minus c2 alpha 2 minus minus cj minus 1 alpha j minus 1 minus cj plus 1 alpha j plus 1 minus cn alpha n. Since cj not equals to 0, that means inverse of cj exists in field, and cj inverse into cj equal to 1, where 1 can be the identity element in F. Now we can divide cj to the whole equation cj alpha j equal to beta minus minus cn alpha n. We have alpha j equal to cj inverse beta minus cj inverse c1 alpha 1 minus cj inverse c2 alpha 2 minus cj inverse cn alpha n equal to p1 alpha 1 plus pj minus 1 alpha j minus 1 plus pj beta plus pj plus 1 alpha j plus 1 plus pn alpha n, where pi equals to minus of cj inverse into ci if I equal to 1 to j minus 1 comma j plus 1 comma n equal to cj inverse if I equal to j. Thus alpha j is a linear combination of the vectors alpha 1 alpha 2 alpha j minus 1 beta alpha j plus 1 alpha comma alpha n. We first prove that this set is linearly independent, and furthermore we will show that this is also a spanning set. These two imply that the set will be basis of V. That means beta can be included in the basis, and beta basically replace alpha j. That's why it is called replacement theorem. Beta replace alpha j here. Now let us consider the relation d1 alpha 1 plus dj beta plus dj plus 1 alpha j plus 1 plus dn alpha n equal to theta. For some scalars, di belongs to f, I equal to 1 to n. Then d1 alpha 1 plus d2 alpha 2 plus dj minus 1 alpha j minus 1 plus dj into beta can be replaced by c1 alpha 1 plus c2 alpha 2 plus dot dot cj minus 1 alpha j minus 1 plus cj alpha j plus cj plus 1 alpha j plus 1 plus dot 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 cn alpha n, and plus dj plus 1 alpha j plus 1 plus dot 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 dn alpha n equal to theta. Theta means 0 vector. Or you can take the components of alpha 1, alpha 2, alpha j minus 1, alpha j plus 1 and alpha n separately. That means uh, the coefficient of alpha 1 is d1 plus dj c1. Coefficient of alpha 2 is dj c2 plus d2. Coefficient of alpha n is dn plus dj cn. Now, as the set alpha 1 dot dot alpha n is linearly independent, that means t1 plus djc1 equal to 0, comma d2 plus djc2 equal to 0, comma dot 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 dj minus 1 plus dj cj minus 1 equal to 0, and dot 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 dn plus djcn equal to 0. Now dj cj equal to 0 implies dj equal to 0, as cj not equals to 0. It is given. Therefore, di is equals to 0 for all I equal to 1 to dot dot n, which proves that alpha 1, the set alpha 1, alpha 2, alpha j minus 1, beta, comma alpha j plus 1 dot dot alpha n is linearly independent. We now prove that linear span of this set is also equal to V. Let S equal to alpha 1 alpha 2 dot dot alpha j minus 1 alpha j comma alpha j plus 1 dot dot alpha n, and t equal to alpha 1 alpha 2 dot dot alpha j minus 1 comma beta comma alpha j plus 1 comma dot 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 alpha n. Since beta is a linear combination of the vectors of S, each element of T is a linear combination of the vectors of S. That is, L of T means linear span of T, subset of span of S. Now, since alpha j is a linear combination of the vectors of T, each element of S is a linear combination of the vectors of T. That is, span of S is subset of span of T, which means that both the spans are equal. That means L of S equal to L of T, which is equal to V, and which proves that the set S is nothing but linearly independent as well as span the whole space V. That's why the set S forms a basis for the vector space V, which means that the new set uh, in which beta includes and alpha j excludes is also a basis for V. That means beta can be replaced alpha j in the basis, which was the proof of the theorem. Thank you.